Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome you all in lecture number 4, right? So, in lecture number 3, basically, in lecture number 1, we start the design, the theoretical design, and the analysis and design of doubly reinforced beam. In lecture number 2, we do some examples over it. While in lecture number 3, we also do some example, right? One example which is in very in-depth detail, right, of the design of the doubly reinforced beam, right? Now, here in this lecture, which is lecture number 4, we will do the and another example, which is example number 5.10. But before start this example, I must recommend you that please watch lecture number 5, because this is a sub part, you can say, of lecture of the lecture number 3. Okay, because we already covered in full detail this example, right, which is more than 1 hour. Okay, that lecture number 3. And here you can see that this example is also um, maintaining the same steps as we do in this example. So that why you must watch that lecture number 3, then watch lecture number 4. Now in lecture number 4, we have to code this example 5.10. So what we have in this example, the data is already given to us that B is 15 inches, D is 20 inches, D prime is 4 inches, MD is given, ML is given. Remember, the example is chosen from the MC Cormac book, right? MC Cormac. The most easiest approach which is followed in this book, right? While if you are going and watch and read the W reinforced beam design in Nelson, in MC, in McGregor book, so they are a little bit complicated for the students, right? So this book basically give you a very simple and unique design and analysis from the W reinforcement. That's why I'm choosing the example from this book, right? So ML, MD, FC prime, FY, already the details are given. So what we have, select the reinforcement. First of all, as we did in that lecture number, in example number 5.9, we basically, what we do, we we calculate the moment capacity. First of all, remember, we have to design the section as singly reinforced. We have to find out the AS1 value, right? We have to find out the S1 value. So find the value of S1. We assume that, let's say, we are using the value of rho max. Why we are using this rho max, I already explained the reason in that lecture number 3. And once you find out the value of 0 rho max, that is 0.85 fc prime divided by fy into beta 1 into 0.003 divided by 0.003 plus 0.005. So from this you calculate rho max, and from this rho max you will calculate AS max, which is equal to AS1, right? So here we will have rho max equals to BD, right? So from here you find out AS max. After that you find out the moment capacity, M in 1, which is denoted by M in 1, right? Phi M in 1. Now here you have phi value, that is AS max into Fy into D minus A over 2, right? So from here you calculate the value of A. A is what? A is equal to AS max, or AS1, times Fy divided by 0.85 Fc prime, right? So into B. So we will calculate the value of A, and you find out the capacity. Now you have to compare this capacity with the mu. If mu is greater than this value, m in 1, this means that the section capacity is not enough to support this moment, and we need a doubly reinforced beam analysis. If architect, basically they bound you that you have not to change the b and d value. Okay, these values are fixed. So that why in that case you have to go for the doubly reinforced beam. So let's start the example. We calculate the mu value as usual. We got the value of 564 fit cap, right? And now let's say we are assuming p value is 0 0.9. Okay, this is the first assumption, remember. And we in later stages we will check whether the phi value 0 0.9 is okay or not okay. We will find out the mn, that is the nominal moment capacity. Don't need it this stage, but let's say we will calculate mn is equal to 626.7 feet cap. S max, as I already explained this, S max is also equals to S1. At this stage we can write this, that let's say S max equals to S1. Now find out the moment capacity as I already explained in this formula, and we find out that 410, which is less than mu. Okay, mu is what? Mu is 564. So this means that we need double reinforced beam analysis. We need to find out the mn1 value. So how to find out mn1 value is what? And that is the capacity 410. 410.4 divided by phi value 0 0.9, just divide it, you will got the mn1 value, right? And then we need to mn2. So mn2 is what? Mn minus mn1, right? So already we calculate mn value, that is 626.7. So now you see the mn2 value is 170.7 fit cap, right? Checking the assumption. Now again I already mentioned in that lecture number 3 that we will assume this value f equals to fy equals to fs prime, and in later stages we will check whether fs equals to fy or not. Okay, so first of all we will use this assumption. By using this assumption, the, why we are using this assumption, this is also important because it simplifies that s prime equals to a is 2. This is the reason that why we are using this assumption. All right, so here we have, let's say we are assuming fy equals to fs prime. So calculate the c value a divided by beta 1. So you need a value, and a value is already calculated, this is 6.39 from this equation, right? And you just divide it by beta 1 0.85, you got 7.52. Now check the fs prime value, I already explained this in both in those three lectures. So now this is the stage that here we have attention, right? Because I already mentioned that you have to check your fs value whether it is equal to fy, whether fs prime is greater than fy, whether fs prime less than fy. If it is satisfied, this means balance failure. We are okay. If it is greater than, so it is also okay. This is ductile behavior. But at this stage, this means your compression still is not yielding, right? So how to ensure a ductile failure? This is the this is in another uh, type of problem, right? So assumption is not valid. This assumption is wrong, and we have to calculate the A is 2. Now the assumption which we basically use this assumption, by using this assumption we can say s prime equals to s2. But now as we see fs prime not equals to fy, this means what? This means that you have to calculate the as2 value from the relationship as prime fs prime divided by fy, right? So by using that relationship, as you see here, as prime required, um, now you can also say that yes, theoretical s prime. Now we need to find out s prime value because we don't know the value of s prime, so we need s prime value. So how to calculate s prime value? So s prime value will be calculated from, because s prime is the compression reinforcement, and the compression reinforcement will take the value of mn2, not mn1. Remember, mn1 value is taken by the s1, right? So that why s prime, for s prime you have to just plug mn2 value, right? And fs prime d minus d prime you already, but note it right here, we are using the value of fs prime, not the value of fy. Remember, in already in other stages, if you see in the other examples, right, let's say in example number 10.9, when we are calculating the as prime value, already I think so in that stage as prime equals to as2, so we don't need to calculate because our fy equals to value is already satisfied, that fy fs prime equals to fy. But if it not equal, remember, then you can't use fy here. You have to plug. Remember, this is very very important, right? This is very very, you have to use fy value, not fs prime value, not fy value, right? So you have to plug the actual value, that is 40.6, not the 60. So here we have 3.15 inch. For this reinforcement we use 4 number 8 bar 3.14, a little bit lower value. Okay, this is also very important point, right? So again we are using the relationship as to, remember from this is why we are not using that s prime equals to s2, because fs prime is not equal to fy, and that's why we have to use, in that example basically we don't use this check, we don't use this relationship, because here you see fs prime is greater than fy. That's why we can say that our as2 is equal to as prime. Okay, as2 equals to as prime, because our condition is satisfied. Here you can see, but here the question is different. Here the actual value is 40, which is less than fy. So that's why we are using this relationship, and from this relationship we got as2 2.12, and again as s1 plus s2. We already know s1 and s2 because we calculated s1, which is right, this one, and s2 is already calculated 2.12. Okay, so s2 and s1 will give you s value. Now we need to check the capacity of the section, whether it is satisfied or not. So for this reinforcement, 7.55, what we have to use, uh, that is 7 point, we will use 6 number 10 bars, right? 6 number 10 bars. This is important. Okay, 6 number 10 bars. Now we will checking the value of 0.9, whether 0.9 is okay or not okay. Okay, because we check fs prime value, which is not okay, so we will check epsilon t. So from this relationship, okay, 20 minus, now here is d, right? This is d value, we already know this, d minus c divided by c, and we need a value, right? Because here you can see c, and to calculate c we need a value. So how to calculate a value? This is as minus as2 into fy into 0.8, as usually we do in 10.9 example, right? So as already given, as2 is calculated 2.12. Remember, we are using the actual values. 7.59 is the actual value, as2 2.12 is the calculated value, we already calculated it. So okay, this is important. Here from here is to 2.12, right? Not 3.14, right? This value is 2. This is very important. So the a value is this one, right? C value, a divided by beta 1, we got 7.58 inch. Now a is 1, a is 1, a is 1 is what? 7.59 minus 2.12, this is 5.47. Now see, here you see S1 is 5.43, but due to the improper bar selection, because practically you can't choose such bars which exactly give you this amount of steel, alright? So that's why it will change the value of S1, because we choose 6 number 10 bar which give us 7.59. Theoretically we needed 7.55. So that's why we are increasing the reinforcement. Due to this increase, it will affect the S1 value, right? So the exact value of S1 is 5.47. Now, once you got the C value, just plug the C value right here. You find the epsilon T value, which is 0.00491, which is less than 0.005. So from formula, which is I already explained in lecture number 3, that P value, when your epsilon T value is less than 0.005 but greater than 0.002, you have to calculate the p value from the relationship 48 plus 83.3 into epsilon t. You just plug the value of epsilon t you find out this p value, which is right here, 0.896 from formula. Now you just calculate the moment capacity, and the moment capacity, we already know this equation. This is for tension reinforcement and this is for compression reinforcement, right? So we see that, right, the moment capacity 559.73, which is less than 564. Already we are close, but if you want to adjust this, use the same procedure as we did in that example right here. Same steps you have to follow right here, because I already explained this in that lecture number 3. So please go there, watch that lecture, and the rest of the calculation is same. To increase the capacity, increase S prime value by an amount of this much, you will close to your required results, right? Now the next example is, let's see, we will discuss it. This is, I think so, this example is from the Nelson book. uh, you see here, mu is already given, h is given, b is 24 inches, see, d prime is 3, fc prime 4 ksi, fy is 60 ksi. So what we have to do, we have to design the beam section. Again, the d value is word 16. This is the total depth, okay? Because you see, the depth is 16 inches. This is 3 inches, and the total depth is how much? 16 inches. Very small amount, right? This is 16 inches, but the depth is, the width is 24 inches. Okay, so this is how. First of all, we need to calculate S1 or S max. We have to check whether it is a single reinforced beam, whether it is a double reinforced beam. So again, the same procedure as one. A value, find out the capacity mu or mn1. Mu is greater than 5n1. Need a double reinforced beam analysis. Find out mn, find out mn1, and then mn2. Right? And once you calculate mn2 value, now you have to checking compression steel is yielding or not yielding. You calculate the A value from as1 fy divided by 0.8 prime. This is this one. Using C value, calculate the C value. Now use the equations of Fs prime, which is 0.85 Fc prime divided by Fc prime divided by Fy into 0.00. Okay, so here from this equation, sorry, that equation is used for rho max. Sorry. Now Fs prime, recalculate the value of Fs prime. Okay, so Fs prime 87,000 or 87 C minus D prime divided by C. Okay, so you got, this is divided by 1000. Okay, because if you are using 87,000, then it will use the pounds. So divided by 1000, it will give you KSI, right? So we already know the value of CD prime is already given. S prime required, as we did in previous example. Remember, this is less than Fy. This is interesting, right? So that's why we have to calculate S prime, and in using S prime value, when you are going to calculate, we have to use the actual value of Fs prime, not 60. Remember, so Mn2 and Fs prime. Remember, these two are very important because most of the students do this mistake. They used Mn1, they use Fy value. Okay, so 4.85 inch square. Again, we need a, so for this bar, remember, for this bar, we provide 6 number 11 bar 4.84 square inches. Now S2, which is the actual reinforcement, S2, S prime Fs prime divided by Fy, that is 2.71 square inches, right? Now we need as, as1 already calculated, as2 is this one. We provide this. For this reinforcement, we have to choose the bars 14 number 7 bar, right? And now again recalculate the a value. From this value, remember, s minus s2 divided by 0.8 c prime into b, and remember we are using fy because a value is calculated for the tension, so don't take tension for the value of fy, not you have to use fs prime value right here. Okay, always you have to, when you are going to calculate the a value, you have to plug Fy value, not Fs prime value. Okay. Now C value, right, and epsilon T value is 0.00. So again it is less than. So recalculate the value of phi value, that is from the same equation, 0.89. Now plugging this value right here, phi mn1 plus phi mn2. We know about the mn1 is the capacity of the tension reinforcement, mn2 is the capacity of the compression reinforcement, but multiply this time by 0.89, not by 0.9. Okay, and here we have, it is 4761 and 4800. So here we also closed, but as the actual value is less than, the capacity of the section is less than the moment, the ultimate moment capacity, so we need to increase the bar section, increasing steel bar area, or Fs prime value or Fi value. We have three different options. Okay, there may be some other options. Okay, but as in example number 10.9, lecture number 3, we discussed the three possible arrangements. We can't use the first arrangement because we are bound here. We can't change the dimension. We can increase Fy and Fc prime value, and we can increase the value of the steel reinforcement. Okay, as we increased in lecture number 3 for the example number 10.9. So I hope these examples mm, will be enough for you people. If you have still some doubts, some questions regarding the doubly reinforced beam analysis, I welcome you all. Please share your questions, right? And I will also search some other examples, okay, from various books, because I have different books I'm studying. Okay, so like this book, there are also some other examples, but all books using different approaches. Although as a student you have to use only one approach, and I think I suggest the MC Karmic book, which is the more efficient, more simple one for the design of the double reinforced beam. Thank you for watching. See you in next lecture.